Okay, so just a quick review of yesterday with inclined planes. Okay, so yesterday we learned how inclined planes work. Okay, we learned how inclined planes work. Okay, we said that this angle, okay, is going to be, well, present obviously, and then we're going to have our mass in here, whatever it is in kilograms. Let's just say it's 100. Okay, the forces involved are gravity, trying to pull the box straight down. Okay, normal force, which we're not really concerned with yet, okay, that's acting straight out from the surface, and then that they add up to, as a net force, at F parallel. Okay, so F parallel always acts down the plane. It's the force that's pulling an object down the ramp or down the plane or down the hill. Okay, and then there could be various other forces. There could be friction. If the object is moving down the hill, friction is acting which way? See people doing this. Somebody say something. Up the hill. Okay? Friction would be acting up the hill if the object is moving down the hill. If the object is moving up the hill, friction is acting down the hill. F parallel always acts down the hill. Okay? Because that's the way it points. We solve for it using this triangle. It can only ever point down the hill parallel to the plane. Okay? There could also be applied forces. Okay? That could be someone pulling or pushing the box up or down the ramp. I don't know why anyone pushed something down a ramp, but if they did. Okay? Now, is it possible that I could lower something down a ramp by pulling up? It is, right? As long as the force down is greater than the force up, the object still moves down the ramp. Okay, I was giving you the example yesterday that every spring and every fall I build a ramp to get the generator out of my truck. Okay? In the case when I'm lowering it, I still pull up the ramp. Okay? I just don't pull as hard as gravity pulls down. It's much easier to get it out than it is to get it in, okay? Because I don't have to exert as much force to lower it down the ramp as I do to pull it up the ramp. Okay? So these are the little things we gotta kind of watch for, read questions carefully, and visualize when we're doing any kind of Newton's law problem, Newton's second law problem. So what I want you working on today is 2 worksheets from the digital workbook, but I don't want you to do them in order. I want you to go back and forth between them. Okay, the 2 worksheets are called, okay, the first one is the inclined planes worksheet, and the second one is the force as a vector quantity worksheet. Okay, so they are on pages 3 and 4. So what I want you to do is just kind of go back and forth between them. That way you're not doing like 15 inclined plane problems in a row. Okay, the force as a vector quantity worksheet has lots of different kinds of problems, but more often than not, I put an inclined plane question on your unit exam. Okay, that said, I also put other kinds of Newton's second law questions on there, but I almost always have an inclined plane question on there. So what I want to do is, I first off want to look at number 1 from the force as a vector quantity worksheet together. Okay, and then we'll look at, then I'll leave you guys to work on this for a bit because you just need some practice at this point. Okay, so question number 1 looks like this. I have a tow truck that's pulling a car behind it. Friction is opposing with a force of 500 newtons. The mass of the car is 1,500 kilograms, and it's being towed at a 45-degree angle by 2,000 newtons worth of tension. Okay, so is this a fairly involved free body diagram? Like, it sounds like it, for sure. Okay, so I have to read the question carefully. Not to draw the diagram, but to understand what's going on. Okay, and so I have a 1,500 kilogram car, and it's being pulled, okay, towed along the ground. It's pulling behind it. So the car is only moving which way? Like when a tow truck pulls a car, which way does the car move? Forwards. Okay, it might be tilted like this, but it's still just moving forwards. And that's something I have to realize when I answer this question. So I've got the force of the cable at a 45-degree angle, 2,000 newtons. Okay, which way is friction acting? Yeah, straight back. That's why I have to realize the car is going forwards. Friction always directly opposes movement. So I have to figure out which way the object is going and then put friction in so I know which way friction is opposing. Okay, so friction is 500 units. Okay. What are the other forces here? What's that? So I've got tension in here already. I've got friction. What other forces are present?
You have to figure out the applied force from the car.
Well, that's right here. This is the applied force from the car. What force is that? Gravity. Okay. The car is moving horizontally. Do I need to worry about gravity and normal force? What do they do to each other? Yeah, they actually don't directly cancel each other, but this is an angled force. That means it has a horizontal component and a vertical component. Okay, so if I'm only looking at this free body diagram in terms of just the vertical forces, I would have the force of gravity and those two forces acting up. And they all add up to what? 0. Car isn't moving vertically. Okay? So even though this force and this force might be present and this force might be present, they're not important because the question told me that the car is moving only in a forward direction. So in that way, this force is only important in order to get me what? Yeah, the horizontal component. Okay? The car isn't moving 45 degrees above the horizontal, it's moving horizontally, which means I only need to know the amount of that 2,000 newtons that's actually pulling forward. Okay? This is that force as a vector quantity thing. Okay? I have to understand that even though I'm pulling this way, the car's not going that way. It's going horizontally, which means I'm only worried about this force, its horizontal component, and the force that's directly opposing that horizontal component. Okay? Again, this is all that visualization, understanding how things work. Okay? And that only comes from practice. It only comes from being exposed to a whole bunch of different situations in which Newton's second law applies. Okay? I can't possibly cover them all, but hopefully as you see more and more, okay, you start to be able to understand what forces might be involved and what parts of them you might need and so on. Okay? So in order to get this horizontal component, I'm just going to go cos of 45 times 2,000. Okay, so 1,414.21. Okay, so I've got 1,414 newtons going forward. I've got 500 newtons going backwards. Okay, and I calculate my net force now. Okay. So whenever we're doing a problem like this that involves vectored forces, okay, I don't want to have too many angled ones. If I can find their horizontal and vertical components, it really makes my life a lot easier in terms of figuring out what's going on. Just like it did in the last unit, finding x's and y's and putting them together. Okay, so F net's going to be 1,414.21 plus negative 500. Okay, so vector sum of all forces here should leave us with 914 newtons, right? I think, yeah, 0.21 newtons. Okay, worth of net force. Okay, then I calculate acceleration by using F net equals m times a. And it was 1,500 kilograms. Okay, so that should give us 0.609 meters per second squared. Okay, so again, we had 3 calculations in that, none of which were really difficult. But what was tricky and what took us the most amount of time was talking ourselves through the forces involved, which ones were important, what parts of them were important. Okay, All right, so I want you working on those, and if you have problems with one, just ask. We'll go through it together. Okay, I'm hoping we're going to go through a lot, and that you're going to keep me very busy up front here. Okay, and that we're going to go through a lot of the questions. So don't be shy about asking. Can you do Mr. Bear? Can you do number 3? Can you do number 4 from the inclined plane? Whatever. Let's go through as many of them as we need to. Okay. All right, so number 2 from the inclined plane worksheet has a 2,000 kilogram truck sliding down an icy hill that's inclined at 20 degrees. So we've got a 20-degree incline. We have a 2,000 kilogram truck. Okay, the force of friction is 500 newtons. All right, so friction has to be acting up the ramp or up the hill because the question tells us the truck is sliding down the hill. Okay, what force is pulling it down the hill? F parallel. That's always the force that pulls something down the hill. Right? So I've got to find that force. And I've got to find that force using the little triangle we always use. Okay, so this is Fn. Okay, this side here will be F parallel. This angle is 20 degrees because it's always the same as the incline. And this is the force of gravity, right, which will be 19,620 newtons. All right, so we're looking for the acceleration of the truck. In order to get the acceleration of the truck, I am going to need F net. And I don't have it yet. But, okay, I can find it if I find the net force using the vector sum of all forces, which would be F parallel plus the force of friction. Okay, so I'm going to find F parallel. F parallel is the opposite side of that triangle. So I'll go sine of 20 times 19,620. All right, so we're looking at 6,710 newtons. Okay, going down the hill, 500 newtons going up the hill. But this would be a situation where something would slide down an icy hill. Okay, there's not very much friction. Okay, that ice is very, very slippery, obviously. Okay, and there's a fair amount of force pulling this thing down the hill. So my net force, using the vector sum of all forces, will be 6,210 newtons plus negative 500 newtons. I'm going to make up the hill negative because forward is down the hill for me. That's the way this question is working. Okay, you could have done it opposite. That's fine. Okay, sorry, 6,710. So that's going to give us 6,210 newtons worth of force down the hill. Now that I have that, now I can use m times a. All right, so my acceleration will be 6,210 divided by the mass of the truck, which is 2,000 kilograms, and that will give us our 3.11 meters per second squared down the hill. And the other one's given a show. Marks.
Number 3 and the forces vector quantity.
Number 3 and forces of vector quantity. Okay. All right. So this is like the one we did yesterday, sine hanging by 2 cables. Right. So we've got the sine has a mass of 55 kilograms. Okay. Each cable is attached to a wall, and the cables hang at 35 degrees from the wall, so they're equal. Okay, we're looking for the tension in each cable. So here's what I need to look at. Obviously, there's a force of gravity acting downwards on the side that I should probably calculate right off the bat. So 55 times 9.81. 539.55. Okay, 2 cables are attached to this sign. They are what's keeping the sign from falling. They're pulling somewhat up and somewhat to the side. And since they're angled equally, they're doing it in the same way. So how much of that 539.55 newtons of gravity is each cable holding? Half. That's the key. Because I have to recognize that each one of these cables is pulling to the side and up. And that vertical component of each cable is 1/2 of the force of gravity. Okay, so divide that number by 2. Okay, so 269.775. Okay, there's my vertical component for each cable. Now that I have that, I can calculate the hypotenuse, which is the tension in the cable and what the question wanted, doing a trigonometry calculation. I have the adjacent side, and I'm looking for the hypotenuse. So the cos of 35 degrees equals 269.775 divided by the tension in the cable. So I simply cross multiply these two things. Tension will be 269.775 divided by the cos of 35, and that should give me my 329 newtons at 35 degrees from the wall or 55 degrees from the horizontal plane. Okay, any other ones?
The inclined plane number 4.
Inclined plane number 4. Okay, what are the key words in inclined plane question number 4?
Constant velocity.
Constant velocity. Okay. Anytime I see those words, I know F net is 0. Okay, so that's one of the things I want to write down. F net equals 0 newtons. Okay, so it's being pushed up a hill. Not a very steep hill. Wow, that was terrible. Okay, 9-degree hill, so it's not very steep. Okay, I'm looking for the mass. Okay, but it's being pushed at a constant velocity. Now I know that friction is opposing with 100 newtons. Since it's going up the hill, friction must be down the hill. Okay, and the force up the hill is 800 newtons. Okay, what's the other force involved here that I don't have on my diagram? What force acts down every single ramp, hill, or plane? F parallel. How big is F parallel? No, I mean like actually what number is it? 700 newtons. Okay, how do I know that? Because the net force is 0. If I have 800 newtons up the ramp, I have to have 800 newtons down the ramp. That's how I know that. Okay, that's why this constant velocity was such a big deal. It told me that the forces up and the forces down cancel each other completely. So if there's 800 up, there's 800 down, and I know 100 of the down was friction. That means the other 700 has to be F parallel. They're the only forces involved. Okay? Nope, it can move up at a constant velocity, as long as it's not accelerating. Right? If there's a net force, it will accelerate. Right? So if let's say, if I want to accelerate my chair, right, I put more force on it than friction, right? Now it goes. Now, as soon as it leaves my hand, it's also undergoing a net force from friction. Friction is the only force acting, that's why it comes to a stop. Okay? But if I want it to go at a constant speed, then I just do this. And I make sure I push with the same amount of force as friction is resisting with, and the chair moves at a constant speed, whether it's up the hill or on the flat surface. Yeah? Okay? Net force is still 0 in that situation. All right, so F net is 0, so that means F parallel is 700 newtons. Now that I know that, I can go to this internal triangle. Because now I know one side of it. I know F parallel is 700 newtons, and I know the angle inside is 9 degrees. Can I find the force of gravity? And if I find the force of gravity, can I use that to get the mass? That's a pretty convoluted question. get you that, okay? There's a lot of steps to that one, okay? A lot of really convoluted reasoning that goes on in there, okay? But anytime you're asked to find the mass, you're gonna have to use the force of gravity to get it, okay? Because you won't be able to calculate the net force without mass, okay? Using m times a anyway, okay? So you'll calculate the net force using sum of all forces and then use one of those forces to get mass from there, okay? And that's what's going on in this one. Okay, so I'm going to find Fg, okay, by going F parallel divided by the sine of 9 degrees. So that'll be 700 divided by the sine of 9. So there's my force of gravity. If I divide that by 9.81, there's my mass, 456 kilograms. Okay, any other ones giving us trouble? Well, if I would have picked ones that gave us trouble, those would have been the ones I picked. That's why they already had solutions on them that I had to erase. They always get asked.
Can you do number 4 for forces of vector quantity?
I sure can. So 4 from forces of vector quantity. Oh yeah, the fish one. Okay, so we have this fish that's being reeled in by a fisherman. So okay, thank you. Okay, so the fishing line is at an angle of 45 degrees from the water. So okay, friction is opposing with 800 newtons if the fish is moving horizontally. Why is that important? It doesn't what?
Gravity doesn't come into play.
Gravity doesn't come into play, and it tells me that friction acts straight backwards on the fish because the fish is moving straight forwards. All right, so friction is 80 newtons. Okay, fish is moving directly forwards. We're looking for the tension in the fishing line. Here's the other thing. Moving horizontally at a constant speed. What's my acceleration? What's my net force? Okay. If my net force is 0 and I got 80 newtons resisting, how big is this side right here? 80 newtons. That's that whole, again, net force was 0, so my vector sum of all forces is 0. I have to have 80 newtons acting directly forwards because I've got 80 newtons acting directly backwards. Okay? Now, I have one side and an angle. Can I find the tension in the line? Right? I'm looking for the hypotenuse now, okay, of this triangle. That'll be the tension in the line. So just a trig calculation from there, okay, using cos of 45 equals 80 newtons divided by the tension in the line. Okay, manipulate, and we've got it. Right. So again, guys, like, not much math there. One trig calculation, and that's it, really. Okay, but there's so much that we have to see, and that's why we have to do so many of these. Okay, any other ones? Okay, keep going then. You guys are doing good. Okay, so this is our first one that's going to involve us doing a vector diagram. Okay, because we've got two angled forces here, or two forces that are not acting in the same direction, and net force is still the vector sum of all forces. Okay, so they're making a snowman, pushing the snowball into position. So I'm first going to draw a free body diagram of the situation. Okay, we have the snowball is 50 kilograms. Okay, and it's being pushed 130 degrees, or sorry, 130 newtons at 15 degrees west of north. Okay, so here's north. There's our 130 newtons, 15 degrees, and the other one is due west. Okay, so that's my free body diagram. Other than identifying the forces, it's not all that useful to me in this question. What is going to be useful is the two vectors being drawn as vector diagram. Okay, so I'm going to have, here's due north, okay, 15 degrees west of north. Here's X, here's Y. This is 130 newtons. Okay, the other kid is pushing due west 110 newtons. Okay, that means that the snowball is going to move this way as a result of those two forces. Everybody okay with that idea? Okay. That force is my net force. So when I do a vector addition thing in this unit, I'll be calculating F net instead of displacement or velocity, like we did in the last unit. The math of it is exactly the same. All that changes is I end up with newtons instead of meters at the end. Okay? So this will be Y, this will be X, okay? And we got to find all of our X and Y components. So black X is my opposite side, so that'll be the sine of 15 times 130. So that side's 33.646 newtons, and that will be west. And my Y component is the adjacent side, so it would be the cos of 15 times 130. And so 125.57 newtons north. And then obviously my green one only has a X component. So that will mean that blue X is going to be 110 plus the 33.646. Okay, so we'll have 143.646 newtons west. And my Y component will be 125.25 57. Didn't even write it right, 57. Okay, 125.57 newtons north. Now that I have those, I can use Pythagorean Theorem to get my F net. Okay, so F net will be the square root of 143 squared plus 125 squared. Okay, obviously with all the decimals. So okay, so my net force is 190.79 newtons. Okay, now that I need to get a vector on that. Okay, so theta will be tan to the minus 1 of the opposite side, 125, over the adjacent side, 143. And that'll come out to 48.8 degrees, and that will be west. Actually, sorry, mine will be 42.2 degrees north of west. Okay, and then obviously it could be west of north if you drew it the other way. Okay, and then I've got to calculate my acceleration. So I'm going to take my net force divided by the mass. Okay, so that'll be this number here divided by 50 kilograms. Right, we get 3.82 meters per second squared. Okay, so simply a vector addition question. Right? Nothing that you would have even batted an eyelash at in the last unit. Okay, but it's the first time we've done one that actually involved us drawing a vector diagram in this unit. Okay, any other ones giving us trouble?
Calculate the acceleration.
Pardon me?
Did you calculate the acceleration?
I did. I took the 190.79 and divided it by the mass, 50. Okay, so my net force, remember, was my result.
Yep.
Okay, divided that by 50 kilograms, so F net over M gives me 8. Okay, any other ones there, guys? Okay, keep going.